In this video, we're going to look at hypothesis test for a single population proportion. The following assumptions need to be made in order to complete this test. First, random sampling must have been used. The product of n times p times q must be greater than or equal to 10. And the sampled values are independent of each other. For the purposes of our class, we're going to assume that all of these are true. The first step, we state our hypotheses. Since this is a test on population proportion, all of our hypotheses involve statements with P. Remember that P naught is actually our null value, so that's going to be a value stated in the problem. Step 2, we're going to determine alpha, which will be given in the problem, and then step 3, we'll calculate our test statistic. The formula for our test statistic, z equals p hat minus p divided by the square root of p times q over n. P hat is x divided by n, p naught is our null value, and this is the same as p in our formula. Q naught is the complement of that, so 1 minus P naught. N is our sample size, and X is the number that falls in our specific category. So when we think about calculating P hat for a specific category, X is the number of subjects that fall in that category. Step 4, you're going to find a critical value. This is going to be based on whether or not the test is one-tailed or two-tailed, knowing the value of alpha, and then using inverse norm to find the critical value for the test. You do have the option of using table 7. However, in this video, I'm going to emphasize inverse norm. Make sure that depending on the test, you use the right sign. We're going to use a positive critical value for right-tailed. The critical value will be negative for left-tailed tests, and you're going to have both positive and negative critical values if it's a two-tailed test. Also in step 4, we draw our picture. So we're going to draw our normal curve with our rejection region shaded, and then we're going to place our test statistic on that graph, and so we can make our decision and support it with the picture. The last part in step 4 is to make our decision. We reject the null if the test statistic is inside of our rejection region, which is going to be shaded, and we fail to reject the null if the test statistic is outside of the rejection region. Step 5, we state our conclusion. Let's look at some examples. The drug Lipitor is meant to reduce total cholesterol and LDL cholesterol. In clinical trials, 19 out of 863 patients taking 10 milligrams of Lipitor daily complained of flu-like symptoms. Suppose that it's known that 1.9% of patients taking drugs complain of flu-like symptoms. Is there evidence to conclude that more than 1.9% of Lipitor users experience flu-like symptoms as a side effect at alpha equals 0.01? The first thing that we want to do is identify what parameter we're testing. There's a couple cues in our problem. 19 out of 863 and this percentage of 1.9 give us the clue that we're dealing with proportion. So the first step is stating our null and alternative, which will both be statements about P. That 1.9% is also our null value. So the null hypothesis is P equals 0.019. Again, make sure that you always convert percentages to decimals. The claim is that more than 1.9% of Lipitor users experience flu-like symptoms. So our alternative is P is greater than 0.019. Step 2, we state alpha. Alpha is equal to 0.01. Step 3, we calculate our test statistic. I always recommend writing the formula out first. That way you know what variables you need to find from the problem. The formula for our test statistic, z equals p hat minus p divided by the square root of p times q divided by n. P hat is our sample proportion. which is calculated 19 over 863, which rounded to 3 decimal places is 0.022. P is our null value, 0.019. I just want to point out, we already said that P is equal to 0.019, so when we're down here identifying it, doesn't make any sense to call it something different. Q is 1 minus P, or 0.981. And N is 863, that's our sample size. So we plug these in. P hat minus P divided by the square root of 0.019 times 0.981 divided by 863. Go ahead and pause here, type this in your calculator. The test statistic for this is 0.65, and we're always going to round our test statistics to 2 decimal places. Back. Step 4. Is when we find our critical value and make our decision, the first thing we want to identify is what type of a test this is. If we look, our alternative hypothesis was P is greater than 0.019. So this is a right-tailed test. We're going to draw our curve. And here's our right tail, and I'm going to shade this right tail in. This is my rejection region. I know that the area of my rejection region is equal to alpha, which is 0.01. So now I'm going to use inverse norm. The area to the left is 0.99. To find the critical value. The critical value is 2.326. We're always going to round critical values to 3 decimal places. And now we want to add onto this graph the value of our test statistic. The test statistic was 0.65. If we think about this normal curve, it's centered at 0. So 0.65 is to the right of 0, but less than 2.326, so somewhere around here, which is not inside of that blue shaded region, which represents my rejection region. Since it's outside, our decision is fail to reject the null. Our conclusion, there is not enough evidence that more than 1.9% of Lipitor users experience flu-like symptoms. In 2014, 52% of parents of children in high school felt it was a serious problem that high school students were not being taught enough math and science. A recent survey found that 256 of 800 parents of children in high school felt that this was still a problem. Do parents feel differently today than they did in 2004 using alpha equals 0.05? Initially, we need to identify what parameter Since we're dealing with percents and we've got that phrase 256 of 800, that implies that we're talking about proportion. So both of our hypotheses will deal with P. The 52% represents our null value, so P equals 0.52 is our null hypothesis. And the claim is that we think parents might feel differently today. So our alternative is going to be P does not equal 0.52. Typically, it's very clear if it's a right-tailed test or a left-tailed test because they have to use language such as greater than, less than, more than, fewer than. If that language isn't there, it's typically a two-tailed test. Our second step, state alpha. Alpha is 0.05. Our third step, calculate our test statistic. The formula for our test statistic, Z equals P hat minus P divided by the square root of P times Q divided by N. Identifying the values of our variables, P hat is 256 divided by 800, which equals 0.32. P is our null value, so 0.52. Q is 1 minus P, or 1 minus 0.52, which equals 0.48. And N is our sample size, in this case is 800. Now we'll substitute those values in. Z equals 0.32 minus 0.52 divided by the square root of 0.52 times 0.48 divided by 800. I would pause here, type this in your calculator, and come back and check your answer. The z-score is negative 11.32, rounded to 2 decimal places. Step 4, first identifying that this is a two-tailed test. And that's because our alternative hypothesis is P is not equal to 0.52. We're going to draw our picture, set up our rejection region, and find the critical values. In a two-tailed test, both of the tails represent our rejection region, so those two shaded tails represent the rejection region, and the area in the tails combined is alpha, and the area in each tail is alpha divided by 2, which is 0.025. And now using inverse norm, we can find those critical values. Our critical values are negative 1.960 and positive 1.960. Adding our test statistic is negative 11.32, which is way down here, which is very clearly in our rejection region, so our decision is to reject the null hypothesis. And our conclusion would be that there is enough evidence that parents feel differently today than they did in 2014. In a survey conducted by the American Animal Hospital Association, 37% of respondents stated that they talked to their pets through the answering machine or on the telephone. A veterinarian found the result hard to believe and thought it would be less than this, so he randomly selected 150 pet owners and discovered that 54 of them spoke to their pets through the answering machine or on the telephone. Test the vet's claim at alpha equals 0.05. Again, the inclusion of those percentages and statements of 54 out of 150 imply that we're dealing with proportion, and that original value of 37% is going to be our null value. So we can set up our null and alternative hypotheses first. Our null is at P equals 0.37. Our alternative is P is going to be less than, if we look at our statement, the veterinarian believes that it would be less than this. So it's going to be P is less than 0.37. Step 2, stating our level of significance, alpha equals 0.05. Step 3, we calculate our test statistic. The formula for our test statistic, Z equals P hat minus P divided by the square root of P times Q over N. And next, we'll read through the problem to find the values of those variables. P hat is going to be our sample proportion, or 54 divided by 150, which equals 0.36. P is our null value, 0.37. Q is 1 minus P, or 0.63, and N is 150. We're going to substitute those values into our formula. 0.36 minus 0.37 divided by the square root of 0.37 times 0.63 divided by 150. Go ahead and pause, type this in your calculator to evaluate and find your test statistic. Rounding to 2 decimal places, our test statistic is negative 0.25. Step 4, this is a left-tailed test. Because our alternative hypothesis is P is less than 0.37. Our rejection region is just going to be the left tail of that normal curve. And the area of that left tail is our level of significance, or 0.05. Because this is a left-tailed test, I also know that the sign of my critical value is going to be negative. Using inverse norm, I find that the critical value is negative 1.645. If I were to mark where my test statistic would fall, again, the middle of this graph represents 0, and negative 0.25 is going to be between 0 and negative 1.645. Since that's not in my shaded region, we fail to reject the null hypothesis. Our conclusion is then that there is not enough evidence that less than 37% of pet owners speak to their pets through the answering machine or on the phone.